Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to learn about trees. So let's start with a simple definition for a tree, and then we'll really work through it in this lesson to understand what it means. So trees are made up of connected nodes. We always start at a root node, so in interviews you'll be given this root node. And then to iterate the tree, you have the connected nodes, or its children, which you access from each node to visit those. So a tree can represent hierarchy, where the top is the root, and then we continue to branch outward and downward until we reach the end. Or you can think of a tree as going through paths. The root is always the starting point, but then you can follow many paths and traverse each one until you reach the end. With trees, we start to diverge quite a bit from arrays and other highly structured linear data structures. With arrays, we were indexed, we were linear, which means we had a starting point at the 0 index, and then a single path to the end. With trees, we have very different characteristics. It's nonlinear, which means we start at the root, but then there are many paths we can follow. There isn't a single path from the beginning to the end. It has much less structure, and trees aren't contiguous in memory. All we know is that at any node, it can have children, and then this node tells us where to find those children in memory. With an array, we know its length, so to iterate it, we start at the 0 node, and then use a for loop to go from the 0 to the final length. With a tree, we have no idea what its length is, what nodes are in the tree, or anything else about its structure. We are only given the root node, so then to move to further nodes, we just check if each node has children. So we check for the root node's children. If it has those, we move forward. Then when we reach these lower nodes in the tree, we check for their children. If it has them, we continue to iterate downward. And we repeat this process until we reach a leaf node, which points to null. And as we continue to go through this lesson, we'll see more deeply how this iteration and traversing a tree actually works. Up to this point, we've been a little abstract when talking about trees, so let's look at some real-world examples. And one of the most common, and one you're probably familiar with at some level, is the DOM. The DOM is how we represent web pages. Everything on the page starts from an HTML node, which is the root, and then under that we have further nodes. So we have the head, which represents metadata about the page, and under the head, we have things like the meta tag, the title tag, and the link. So each of these HTML elements are just nodes in the tree. Then we also have the body, and under the body, we can have things like h1 tags, we can have div tags, p tags, and this can go as deep or as broad as we want. It's all about how we build the page, so it's a very loose and unstructured data structure. Everything starts from the HTML node and branches outward and down. So the DOM is a tree data structure that represents the hierarchy of a web page. Another common example is the file system on your computer. Everything starts at a root drive, but then it can branch downward and outward using folders. So we click into folders. These folders can contain more and more folders, and we actually don't know how far down or wide it will go. So we just have to follow the folders to iterate through the file system to find the files that we want. And finally, posts and comments on the internet are represented as trees. So you can think of a Reddit post or a Facebook post. There's an original post, which is the root node, and then under that it can have comments, which are its children, and then each comment can have its own comments. So we have this tree data structure that starts at the post and then branches downward and outward through comments. But to represent a tree in code, it's actually pretty simple. Each tree just contains data, so the value stored in this tree and then some reference to its children. In a broad definition of a tree, any node can have any number of children, so it uses an array. For example, the node with the value number 1 would have 3 children in its array. Or if it's a binary tree, this means it can only have at most 2 children. So we just declare variables to its left and right child. So the node with the value 1 down here, its left attribute points to this node, and its right attribute references this node. So when we're given a root node, for example here with 0, it would have a left pointer that points to another node. So it's this object that just points to additional objects. And then to traverse the tree, we follow the left and right attribute, or the children in the array, to find more objects. And that's how we traverse the tree. We don't know anything else other than an original node, and then we follow the children, where its attributes points to the children, and then these children themselves are made up of the same object type, so then they'll also reference its own children. So this is how we start at the root node and then traverse down each path. We just follow the left and right pointer, or the array, to a node's children, and then follow this child's children until we reach the end, or a leaf node, which instead of having children, it would have an empty array, or both pointers pointing to null. So let's discuss some key definitions and characteristics of trees. Each item in a tree is called a node, and these nodes are just objects. And we saw on the last slide that an object just contains data and a reference to its children. The reference to the children is called an edge. An edge is what connects nodes and how it tells us to find its children. Each tree can have only one single root node, and this is where the tree starts. And we call the items under a node in a tree its children, which is the hierarchy and how we continue to move downward. Then we define the level of a tree as how far a node is, or the nodes on the same level, from the root. So the root is level 0, then its children are on level 1. All of level 1's children are considered to be on level 2, level 2's children are level 3, and so on. And then the furthest level from the root, this is called the height of the tree. So if we start at 0, we traverse downward, and then for this tree, it took at most 5 moves to get to a leaf node, which is level 5. So for this tree, we say the height is 5. And we calculate this using the furthest nodes from the root. And finally, we can see trees are recursive. Trees are just made of smaller and smaller trees, so we call these subtrees. This full tree is our main tree, but then if we went left, we can see we just have another tree. We can see this node with the value b could be considered the root node of this subtree, where it has children to its left and its right. So trees themselves are actually just a special representation of a graph. So it's a graph with constraints. We'll cover graphs in a separate lesson, so for now, let's just understand what it means to be a tree. The first is that the tree can only have one root node. So it only has one starting point, and this root node itself has no parents. And then every edge in the graph, or pointer to the children, is either directly or indirectly coming from this root node. So the root node is the highest ancestor in the tree, and we can reach any other node, starting from the root, by following the paths. In the tree, a node cannot point to itself as a child, or it cannot point to an ancestor of itself. So it must point to children downward. So C couldn't say it's its own child, and it couldn't say B is its child. It must have new children that branch downward. Another constraint is that each node can only have one parent. So we couldn't say B is C's parent, but then also have D point to C. Each node can only have one parent. Another constraint is that all the nodes in the graph must be connected. So we couldn't have items separate and then still consider them as part of the tree. And finally, a tree can have 0 or more nodes. So it can have any number of nodes to be a tree. So let's look at some cases that aren't trees. Here we have a root node and single node A. Trees are allowed to have only one node, but this node points to itself as its own child, which breaks one of the key constraints of a tree and is therefore invalid. This second picture isn't a tree because we see the node B has two parents, A and D, but in a tree, nodes can only have at most one parent. We also see that D is on B's path, so a child can't point to an ancestor as a parent as well. So for this to be a valid tree, we would need to remove the edge between D and B. And then finally, this last picture, it's not a tree because they're not connected. We said that all the nodes in a tree must be connected either directly or indirectly, but these are actually separate. For this to work, this group of nodes and this group of nodes would need to be connected somehow and then also fall under the other constraints of a tree. And one thing worth mentioning quickly is that a linked list can be viewed as a constrained version of a tree or a special implementation of a tree. A linked list is just a tree where each node has one child node, so it can't have many children as the tree over here. So it doesn't branch outward like trees do, it stays linear. So all trees are just graphs with constraints, and then a linked list is just a tree with further constraints. Trees are a broad category of data structure, and a tree itself can use many different implementations. However, in interviews, the most commonly used tree implementation is a binary tree. And what a binary tree does is restricts any node to have at most 2 children. In the broad definition of trees, each node can have as many children as it wants, but in a binary tree, we only have a left and right pointer, which allows each node to have either 0, 1, or 2 children. So as we've seen, trees can take many implementations. The most common in interviews are binary trees and binary search trees, but let's look at some other terminology to describe what trees are in their special constructions. A complete tree is one where every level must be filled except for optionally the last level. And if the last level is not filled, it must be filled from left to right to be considered complete. So we see here the key difference for the not complete and complete tree in this example is that the not complete tree is not filled in from left to right. So this 60 would need to be the left child as we see in the complete tree. A full binary tree means each node has either 0 or 2 children. So we see on the left, the not full binary tree only has one child under this node. So for it to be valid, it would either need to have 2 children or 0 children. And finally, a perfect binary tree is one that is both full and complete. All leaf nodes must be on the same level, and they must be filled. So we see here every leaf node is on the second level, and none of these have children, and each of the parents above it all have 2 children. And finally, let's look at the pros and cons of trees and understand when we would choose it for our data structure. The first pro is that trees are great at representing hierarchy and paths. For example, you could imagine a hierarchy in real life like a company where the CEO is at the top or the root node, and then all the employees come below him. You have managers who have employees below them, and so on. Or in programming, we use trees and its hierarchy to represent things like the web page, where we start at the HTML node and then fill it with nodes downward and across to create the web page. Or we can use a tree to represent paths, where we start at the root node and then can follow its children nodes until we find the location that we're looking for. Another benefit of trees are their flexible size. For trees, we don't have any strict structure or indexing. We just start at a root node and can continue to add child nodes for as long as we want. So we can grow any tree as broad or as deep as we want for whatever makes sense for the problem. You can think of this like in a web page, where we can make it as large or have as much content on the page as we want and nest it in any fashion that makes sense. Or the folder structure on your computer. You can continue to add files and folders as deep or as broad as you want for whatever makes sense for what you're doing. The downside to trees is that there's no constant time operations. If we want to add or remove a node, we must iterate through all n items in the worst case to perform that action. So if we want to represent hierarchy or paths, trees are great. However, if we don't have this hierarchy or we need faster operations, we should consider another data structure. And as we see here, the big O complexity are all linear time O of n because we must iterate through all the nodes. We will see that this slightly changes with binary search trees, which can get log n operations, but binary search trees are so common and such a special implementation that it has its own module, so you'll be able to work through those in another lesson in the course. Thanks everyone, and I'll see you in the next lesson.